Hello everyone, this is Professor Kadiresh from Aerospace Engineering Department, Crescent University. Today we will talk about thermodynamic cycles, under that as standard cycles. As standard cycle analysis is used to perform elementary analysis of IC engine cycles. This is done based on in actual cycle you have the medium is air and fuel or air fuel mixture we call it is. In as standard cycles we assume air as a medium and we have proceeded for making our analysis simple. Assumptions made when you go for as standard cycles will be working fluid is essentially assumed to be air, which is taken as an ideal gas. Combustion process we are not considering. Intake and exhaust processes are also not considered. Friction losses are also not considered, and specific heats are independent on temperature. So, based on this assumption, we are proceeding with a cycle analysis. Basically, this as standard cycles we will be covering today: spark ignition engine following Otto cycle, and diesel cycle engines, which is followed in compression ignition engine or diesel engines. These two cycles we will be covering today. Okay, we will start with Otto cycle. So, Otto cycle means it has to give a net work output. Obviously, when you are looking for a work output, that should be a energy input. So, here fuel energy is taken as an input, which when it is burned it gives a heat energy. Heat energy will be converted into work output. In the thermodynamic cycle analysis, as standard cycle analysis, we have Otto cycle where we have essentially 4 processes. So, we have a process 1 to 2 as a isentropic compression and 2 to 3 as a heat addition process, which is happening at constant volume, and process 3 to 4 which is a isentropic expansion again, and 4 to 1 is a constant volume heat rejection. In the screen, if you look at, if you have a PV diagram as well as a TS diagram. The PV diagram you can see that process 1 to 2 is shown as a S equal to constant, which is a reversible adiabatic compression process. Reversible adiabatic we call it an isentropic process. The process 2 to 3 where volume is constant, where heat addition is happening at constant volume. And 3 to 4 is a process where expansion is taking place, reversible adiabatic expansion, where entropy is constant, S is constant again. And 4 to 1 is a heat rejection process, again it is happening at constant volume. The same processes are explained in TS diagram also. 1 to 2 where entropy is constant, we can see vertical straight line. 2 to 3 is a heat addition process where temperature rises, which you can see from the diagram. So, there is a rise in temperature. And 3 to 4 is an expansion process, isentropic expansion, where again entropy constant, vertical straight line going downwards, and 4 to 1 is a heat rejection process happening at constant volume. Here, when you do the cycle analysis using medium as air, we will be introducing a term called compression ratio. Compression ratio is nothing but the ratio of V1 by V2. V1 is the initial volume, V2 is the volume at end of compression. This ratio we call it a compression ratio. And we are trying to derive an equation for efficiency of a cycle. In that, we will be deriving the cycle efficiency equation in terms of thermodynamic properties, how it can be derived. So, before going to the derivation part, let us discuss Otto cycle. Otto cycle is a as standard cycle, and the actual cycle, what I said, this Otto cycle will be followed in spark ignition engine, which is petrol engine basically. I will explain the Otto cycle first and then connect how actual cycle is followed in a petrol engine, then we will see the differences. The bottom diagram you can see the Otto cycle. So, basically this automobile engines, piston engines will have a piston cylinder arrangement. The piston will have a reciprocating motion inside the cylinder. So, when the piston is moving down, so air will be air fuel mixture you can see here, air fuel mixture is taken inside, and inlet valve is opened, and there will be one more valve like exhaust valve that will be in a closed position. So, air fuel mixture is taken inside and the piston is moving down. So, we call this a suction stroke. Suction process is carried out, air fuel mixture will be rushed into the engine, it is filling this cylinder. So, that is a process. In a thermodynamic cycle, we may not show this suction process and exhaust process. So, what we start is process 1 to 2, we refer it as a isentropic compression process. So, in the diagram, compression process we start with compression process in Otto cycle. Say process 1 to 2 is that when the piston is moving from bottom dead center to top dead center, the compression process is carried out, and we assume this is happening at as a reversible adiabatic compression. So, compression process is carried out. At the end of compression stroke, so we are igniting, the combustion process is initiated. That means we are in actual cycle, fuel air mixture will be taken. At the end of compression stroke, we will be igniting it with a spark plug. So, combustion will be taking place. In the as standard cycle analysis, no combustion is considered. So, we will assume heat is added at constant volume. When the piston is at TDC position, assuming it is remains in that position for a moment and the volume is kept constant, in that condition heat is added. So, that is what shown in Q in. And then when heat is added, it gives so in a real case, in actual case, what happens when the fuel is burnt, it gives a high pressure, high temperature gases, product of combustion, which pushes the piston down. So, a piston will start moving from top dead center to bottom dead center. We call this as an expansion process. So, this is shown in the PV diagram as a 3 to 4 process. 3 to 4 is again reversible adiabatic expansion. And then we will have a fourth process called exhaust process. And as standard cycle analysis, this 4 to 1 process is shown as a heat rejection process, and you can see heat is rejected out at constant volume. Whatever burnt gases available here will be swept out when the piston is moving from bottom dead center to top dead center. So, this is about as standard cycles, and this actual cycle, instead of air we will have a air fuel mixture, because with simple air we cannot add heat addition. Heat addition process cannot be done. When you have a fuel, burning can take place, and then it gives a energy out, thermal energy or heat energy. This heat energy can be converted into mechanical output. That is what happening here. So, we will try to derive the equation for a thermal efficiency. Before that, so there is a slight difference between actual cycle and the as standard cycle, which is a theoretical cycle, we can say. The theoretical cycle, we assume the process 1 to 2 will be taking place as a reversible adiabatic. In real case, no process could be a reversible process, there will be some deviation, and the combustion will be taking place at the end of compression, and it is happening at constant volume. So, this piston, pressure versus volume displacement is shown here, and in the actual ideal cycle we shown it as a straight line, but in the real case it may not be straight, because volume is not going to be constant, because this piston is continuously moving. Piston inside the cylinder will not stay for a moment, it will be continuously moving. So, there will be a slight deviation, and volume is not exactly constant, and moreover ignition will be happening at the end of compression process, theoretical case. In the real case, it will be slightly different. So, just before it reaches the top dead center, ignition will be initiated. So, combustion will take place. So, there will be a slight difference between actual cycle and the ideal cycle, and moreover in the theoretical cycle we analyzed, say that is Otto cycle. This intake process and exhaust process we have not discussed. We started with process 1 to 2, that is compression process and heat addition process, and then expansion or power stroke and the exhaust process. This intake and exhaust process we have not considered for a theoretical analysis, but in real case it will be. So, with this background we will go for the equation derivation for thermal efficiency of a Otto cycle. So, if you look at the thermal efficiency equation, this is work output by energy input. So, work output will be net work done. So, in the net work done we have expansion work and compression work. So, this difference will be net work, and the heat input is the energy input is in the form of fuel energy we are giving. So, that is going to be heat is added at a constant volume. So, W net could be written as Q net from the first law of thermodynamics. So, Q net can be written as Q in minus Q out, heat in minus heat out divided by Q in. Q net can be written as Q in minus Q out by Q. This denominator will be Q in. So, if you rewrite this equation, it will be 1 minus Q out by Q in. Okay, Q in is a heat input, Q out is a heat output, heat rejected we can say. Okay, from the first law of thermodynamics, we will find out what is Q in and what is Q out. Then we will substitute this in our efficiency equation, and so that the efficiency equation can be derived in terms of thermodynamic properties. Fine. So, Q in heat addition is happening in a process 2 to 3, which is a constant volume process. Okay. First law of thermodynamics says it is dq equal to du plus dw, where you can say dq can be written as q 2 to 3. So, process 2 to 3 is the heat addition process, and w 2 to 3 is the work done for a process 2 to 3, and del u is a change in internal energy for process 2 to 3. So, if you rewrite this equation, q minus w will be del u. Okay. And we know that for a constant volume process, work done will be 0. So, process 2 to 3 is a constant volume process where work done is 0. Applying this applying this concept in a equation, say work done W 2 to 3 will be 0. So, what we have is Q 2 3 will be equal to del U 2 to 3. That means, heat transfer, heat addition will be equal to change in internal energy for a process 2 to 3. You know that change in internal energy can be written as mCV delta T. Delta T between 2 and 3. So, T3 minus T2, which is a higher minus lower. Heat input can be given as mCV T3 minus T2, where T3 is a temperature at the end of combustion or end of a heat addition process. T2 is at the beginning of heat addition process. So, mCV T3 minus T2 will give you the heat input value. And similarly, we can find out heat rejection also. Heat rejection is, again we use the first law of thermodynamics to derive this equation. So, first law of thermodynamics says dq equal to du plus dw. For if you are applying first law of thermodynamics for the process 4 to 1, say q 4 to 1 minus dw, which is w 4 to 1 should be equal to del u 4 to 1. Again, it is a constant volume process. In the thermodynamic cycle we are discussing, which is Otto cycle. Both heat addition and heat rejections are happening at constant volume. So, for a constant volume process, work done is 0. So, leaving this work done parameter, then we will have only heat transfer will be equal to del u 41. Again, del u 41 can be del u 41 is internal energy for a process 4 to 1. So, that could be written as mCV T1 minus T4. Fine. T1 is the temperature at the inlet and T4 is the temperature at the start of heat rejection process. Okay. So, Q out you can write it as mCV T4 minus T1. So, if you substitute Q in and Q out in a thermal efficiency equation, so for Otto cycle, so thermal efficiency of Otto cycle could be written as 1 minus Q out by Q in. So, Q out just now we derived this as mCV T4 minus T1, and Q in can be written as mCV T3 minus T2. If you simplify this equation, we will have this. So, mCV get cancelled. So, 1 minus T4 minus T1 by T3 minus T2. So, if you rearrange this equation, if you take T1 out, this will be T1, if you take T1 out, it will be T4 by T1 minus 1 in the numerator. The denominator you can take T2 out, so that this becomes T2 into T3 by T2 minus 1. And we know that for a isentropic process, so here we have process 1 to 2 and 3 to 4, both are isentropic process. 1 to 2 is a isentropic compression and 3 to 4 is a isentropic expansion process. So, if you apply for isentropic process, this relation is known in thermodynamics. For isentropic process, T2 by T1, 1 to 2 is the isentropic process. For a process 1 to 2, T2 by T1, the temperature ratio T2 by T1 can be written as V1 by V2 power K minus 1, where K is the ratio of specific heat, which is Cp by Cv. In some books they may write it as gamma, so it depends. So, you can use any one of this, gamma, either gamma or K. Let me use K representing ratio of specific heat. Okay. So, T2 by T1 could be written as V1 by V2 power gamma minus 1. Remember, we have already defined V1 by V2 as a compression ratio. So, this T2 by T1 can be written as R power gamma K minus 1. So, this can be written. And similarly, for process 3 to 4, which is again reversible adiabatic expansion process. So, T3 by T4 can be written as V4 by V3 power K minus 1. So, here we know that V3 equal to V2 and similarly V4 equal to V1, both are constant volume. 2 to 3 is a constant volume process and 4 to 1 is also a constant volume process. So, here V1 by V2 could be written as V4 by V3, because V1 and V4 are same, V2 and V3 are same. In that case, you can write T2 by T1 can be written as T3 by T4, or if you rearrange this equation, so T4 by T1 can be written as T3 by T2. So, if you look at this efficiency equation, we have 1 minus T1 into T4 by T1 minus 1 divided by T2 into T3 by T2 minus 1. If you look at this equation, T4 by T1 here and it is T3 by T2, and we have just now seen that T4 by T1 is equal to T3 by T2, meaning this bracketed term can get cancelled. So, bracketed term can be cancelled. What remains is 1 minus T1 by T2. What is this T1 by T2? We already seen T2 by T1 as V1 by V2 power K minus 1. Remember, K is the ratio of specific heat, which is a constant. So, T2 by T1 for isentropic process, we can write it as V1 by V2 power K minus 1, and what is required in the efficiency equation is T1 by T2, that is the reciprocal of this. So, that means T2 by T1 can be written as V1 by V2 power K minus 1. So, the reciprocal of this could be V2 by V1 power K minus 1. Remember, V1 by V2 we have already defined as compression ratio. Compression ratio R equal to V1 by V2. So, the T1 by T2 can be written as 1 by R power K minus 1. So, the efficiency equation becomes 1 minus, so you are replacing T1 by T2 as 1 by R power K minus 1. This is the equation, the final equation what we get. Efficiency of Otto cycle can be given as 1 minus 1 by R power K minus 1, where R is a compression ratio, R is the compression ratio, and K is the ratio of specific heat. So, as I promised, the efficiency equation can be derived in terms of thermodynamic properties. If you look at this equation, K is the ratio of specific heat, because specific heat is a thermodynamic property, and R is a V1 by V2. V1, V2 is the volume. Volume is again property of thermodynamics. So, we are trying to derive the efficiency equation in terms of thermodynamic properties. If you look at this equation more closely, efficiency is more dependent on, say here the K is the ratio of specific heats, which is a constant. Only variable here in this equation is R, which is a compression ratio. We have already defined it as V1 by V2. This V1 by V2 gives the size of your engine. So, based on the size of your engine, the dimension, the efficiency can be altered, or if you want to increase the efficiency, we have to increase the compression ratio. For increased compression ratio, efficiency will be higher. You can see here. So, with the efficiency versus compression ratio is drawn here, the graph. If you look at the graph, with increasing compression ratio, there is an increase in efficiency. But there is a limit on this compression ratio. We cannot keep on increasing the compression ratio, and there is a limitation, because it is based on the fuel characteristics. We can see beyond certain number, say normally the compression ratio for a SI engine or Otto cycle engine will be in the range between 7 and 10. If you go beyond that, there is a possibility of auto ignition. So, remember, in the Otto cycle or spark ignition engine, we have to ignite the mixture, air fuel mixture, to initiate the combustion. So before you issue the spark plug, auto ignition of fuel will take place. That leads to abnormal combustion. We call it a knocking effect. So it happens at beyond certain compression ratio values, range of values. So to avoid that, we have to fix we have to limit your compression ratio. So the corresponding efficiency, if you look at, we will have anywhere close to 50 to 60% for a given compression range of 7 to 10, we have a efficiency closer to 60%. This is possible for an ideal case. In a real case, it may be much lower. In the real case, it will be closer to 35%. That's what we are getting. So that's about Otto cycle. We'll stop here today and we'll continue the analysis for a diesel cycle in the next class. Thank you all.